Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll continue these checkpoint questions. So this is a checkpoint for the chemistry 5070. This is part of chemical structure and bonding checkpoint, where the first part of the checkpoint video had focused on specifically on the multiple choice component for questions relating to chemical structure and bonding. So in the second part of this lecture tutorial, I'll go through these theory level or structure level kind of questions involving chemical structure and bonding. And what I can guarantee is chemical structure and bonding will be embedded in various questions, but they will definitely appear in any 14 to 16 years old chemistry assessment, be it O-level or IGCSE or any other curriculum that you're doing. Okay. So this is an example of a question where they show you two ionic lattices. So you need to know the definition of lattice. Alright, so definition of lattice is required in the syllabus. An ionic compound exists as a giant ionic lattice structure, which again is actually required in the syllabus. So have a look at the syllabus exactly, and you can look at you can rewatch the previous lecture tutorial as well on what is meant by giant ionic lattice structure. In essence, these are actually repeated arrays alternating cations and anions because they'll be attracted to each other. So the cations are surrounded by anions. In fact, it goes up, down, left, right, in front, and at the back as well. So it's three-dimensional giant structure. And NaCl will have a similar kind of giant ionic lattice structure, but depending on how many NaCl, how many Na plus and Cl minus you have in your array, they can be different. So here they happen to be 1 Mg2 plus is to 1 O2 minus because the charge cancel out. 1 Na plus is to 1 Cl minus because the charge cancel out. They happen to have the same kind of structure. But what I'm talking about is when you have things like Mg2 plus Cl minus. So you have MgCl2. The ratio, the fixed ratio of Mg2 plus or Cl minus is 1:2 here. It will not necessarily have the exact same structure as these, which have the ratio of the cation and anions 1:1, whereas here is 1:2. Alright? So explain why these two solids do not conduct electricity. So the key thing here really is solid. This is a giant ionic lattice structure. So ionic compounds do not conduct electricity when they are solid because in terms of kinetic particle theory, in the solid state, remember that the particles are actually closely packed together. So what we can say is the ions are closely packed together and not free, or you can use the word mobile, so not free to move around, to move at all, therefore cannot conduct. Okay, so if your electrons, sorry, not in this case you have the ions are fixed, are simply close together and located in a fixed position where they can only vibrate about their fixed position, so they are not free or mobile to move at all, therefore you cannot conduct electricity. Why magnesium oxide has a very high melting point? Melting is to do with solid going to liquid. So ionic compounds are typically solids at room temperature and pressure. Okay, in fact they are solid at room temperature and pressure with very high melting and boiling point, because we need to talk about structure and bonding. Okay, so MgO is the formula, or you can say magnesium oxide. So they don't give you the formula here, but as you can see, 1 Mg2 plus, the charge is balanced out by 1 O2 minus because the lowest common multiple of the electron being transferred, 2 electron loss, 2 electron gain, 1 of each. The formula of this compound is MgO, or you can use magnesium oxide if you like. MgO has a giant ionic structure. We always start from what is the structure. Okay, so the structure of this compound, ionic compound, is it has a giant ionic structure. So melting, what are you breaking? The change is melting, so melting needs to break. What are you breaking? You're breaking strong, in fact very strong ionic bond between what and what? between Mg2 plus and O2 minus. So this thing is not a fixed answer because it depends on what is the compound that they've given you. They've given you magnesium oxide, which consists of Mg2 plus and O2 minus. So your strong ionic bond is between Mg2 plus and O2 minus in the context of the question. Different ions, then you give different ions. All right. So therefore, large amount of energy is required. I think that should be enough. So despite the question doesn't say structure and bonding, you should always give structure, and therefore what are you breaking? Okay, so that's the same trick whether you're in O level or A level. It's always structure and bonding. So next bit, suggest why the melting point of MgO is much higher than sodium chloride. So this one is also structure and bonding, but because this is comparing ionic compound and ionic compound, so this is comparing two ionic compounds. And if you're comparing ionic compound with ionic compounds, there's no need to think about saying the same thing again. Instead, you should be thinking about how is their strength different? How is their strength of ionic bond different? So ionic bond is to do with how strongly attracted is the cation to the anion. How strong is the attraction between the oppositely charged ion? How strong is the cation attracted to the anion? So MgO has Mg2 plus and O2 minus ions. How about sodium chloride? Sodium chloride has Na plus and also Cl minus. Eventually, you will get more natural with this vocabulary that, it becomes natural to you that you can just write NaCl and MgO by simply knowing the charges of the ions that make up the compound. Okay, there's something that you have to get used to it and eventually become better at it if you know your vocabulary. This is your chemistry vocabulary. The more you use it, the better you'll get at it. All right. So by looking at the two different ions, so Mg2 plus and Na plus actually have the same number of electrons. They have neons electronic configuration. O2 minus and Cl minus do not have the same electronic configuration. Cl minus have argon electronic configuration. O2 minus has neon electronic configuration. However, cations are attracted towards anions because of their charges. By looking at the charges, plus 2 is higher charge than plus 1. Minus 2 is a bigger charge than minus 1. So between plus 2 and minus 2, you have a stronger attraction, therefore stronger ionic bond, therefore more energy is required to break, to separate the two ions that are of higher charges than this one. Therefore, your melting point is higher. Think about the differing or the different strength of the ionic bond. Okay, so the bigger charges, plus 2 and minus 2, or somewhere along that line about the charges being bigger on maybe I can re-clarify this. The bigger charges of Mg2 plus versus Na plus and O2 minus versus Cl minus means stronger ionic bond in MgO. So between the Mg2 plus and O2 minus is a stronger ionic bond. You are comparing, when you're comparing something, this is higher than. So comparing something means your answer must compare something as well. Therefore, much more energy is required. Much more energy is needed or is required to melt MgO than NaCl. The next bit is basically a simple dot and cross. This is draw electronic structure of a magnesium ion and an oxide ion. Take note, so note that they did not specify valence shell or electrons. Okay, so if they don't specify draw valence shell or draw valence electron only, that means you have to draw all of them. Okay, Mg2 plus is going to have neon's electronic configuration, so it's 2,8. O2 minus is going to have neon's electronic configuration, so it's going to be 2,8. So I'll start by drawing the Mg first, Mg, and then I know there are two shells because there will be the first shell and the second shell, they will be completely filled outer shell. So I use cross for Mg. You can use dot if you want to, but you have to use cross for the other one. If I use cross for Mg, I'll have to use dot for oxygen. It's called dot and cross, which is alright, I guess, for you. So I draw in pairs because they are nice and easy to count. So the magnesium has lost 2 electrons, so it's no longer magnesium atom. So make sure that you put a 2 plus to represent it as an ion. When you lose the 2 outer shell electrons in the third shell, now your outermost shell is just the second shell. I'll try to use a different color ink to see the difference here. So oxygen, so dot, dot, and then second shell, dot, 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 dot. So oxygen is in group 6, alright, so 1, 2, 3, 4, 5, 6. Group number of oxygen is group 6. Group 6 means 6 valence electrons. As stated in the previous topic, candidates should be able to state that group number of an element indicates the number of valence electron. But you gain 2 extra electrons from the magnesium atom. So that's why I have 2 crosses there that come from the magnesium atom, and I get a 2 minus charge because I gain 2 extra electrons. The stoichiometry, meaning the ratio, the 2 plus charge cancel the 2 minus charge. That means I only need 1 of each. That's why it's Mg2 plus 1, O2 minus 1. That's why the formula for magnesium oxide is just MgO. Okay? And that's the end of that question. So let's get moving with the next question. So these are properties of group 6. So this is 6 valence electron because group number tells you how many valence electron, how many outermost shell electrons you have. Use the information to suggest. It's a suggest, so do not try very hard and think about the value. Just see if it's logical based on the value given. Based on the value given, this is going down the group. The density increases. From here to here is around plus 2. Is it plus 2? Yeah, give or take around plus 2. Meaning to say you add around 2. Here to here, you add probably around 3. So between here to here, I would say between 2 and 3, you should be alright. So if I add around 2, I'll get around 4. And if I add around 3, I'll get around 5. 5 is probably not in between. So if I choose a value in between, I can probably do 4.0, for example. So something sensible, something which is right in the middle, considering that, you know, plus 2, plus 3, I can just a plus 2 and I get a 4.0. Any value which is in between 2.1 and 6.2 should be alright, but you don't want it to be too close to 2.1. You don't want it to be too close to 6.2, okay? Considering where the other data is. For 1 mark, suggestion is a very important skill that you should be able to just suggest a value by looking at the data without thinking too much into am I correct, am I not, because it's a suggestion, all right? Use the information to deduce. Deduce means work out the physical state of oxygen at minus 190 degrees Celsius. Oxygen has a melting point. Oxygen has a boiling point. Remember your topic 1, states of matter. So temperature degrees Celsius. Minus 219 is lower than minus 183. So this is the melting point. This is the boiling point. If it hasn't melted, then it's a solid. If it already boiled, then it's a gas. Anything in between is going to be a liquid. You haven't melted yet, so you are solid. You have already boiled, you are a gas. If you are in between the melting point and the boiling point, you are a liquid. So now, what do we have? Minus 190 degrees Celsius. Put in minus 190 degrees Celsius. Minus 190 degrees Celsius is there. Therefore, it is a liquid. So, minus 190 degrees Celsius is between the melting point, which, you know, you have to use the data in the table. Use the information in the table. So that means you have to incorporate the data in the table in your explanation. I already put in a diagrammatic form. You have to put it into a wordy form so that, you know, all this is in 2 minutes. 2 minutes for 2 marks, so very quickly, all right? Between the melting point and the boiling point. which is -1 at 3 degrees Celsius. So it has melted, but it hasn't boiled. It has not boiled. Alright, describe the trend. Describe the trend in electrical conductivity. So now I have electrical conductivity and I have to describe the trend. So this is not explain, it's simply describe. Okay, so what happened in electrical conductivity? Going down the group. Going down the group, so describing what happened going down the group, it goes from very poor to good. So electrical conductivity of solid increases because it become a good conductor, whereas in the beginning it was a very poor conductor. So they want the trend. Okay, so is it increasing, is it decreasing? All right, so going down the group, so we use the term down group 6, the electrical conductivity increases. Okay, you want to avoid just writing down increases because you are not telling the position. So I'm saying down group 6 because I'm going down. If you just say increase, is it increasing upward? Is it increasing downward? You know, what does downward mean? You're going down the group. Conductivity, electrical conductivity increases. Next bit, there's a trend in the melting point. Okay, which element does not follow the trend? So looking at melting point now, the melting point increases. So this is smaller than this, it increases. This is smaller than this, it increases. This is smaller than this, it increases. And then it decreases. So polonium is the one where it doesn't increase from tellurium. So polonium is the one that does not follow the trend. Okay, so use the data in the table. Again, you have to include data for explanation because use data in the table. So you have to incorporate it. Okay, so from oxygen to tellurium. So from oxygen to tellurium, the melting point increases. From this to this to this to this, the melting point increases. The melting points increase down the group. But after tellurium, so melting point equal to 450 degrees Celsius, that of polonium, so meaning to say the melting point of polonium is 254 degrees Celsius, i.e. it decreases. So just now we say it continued to increase, but then down to polonium from tellurium, it decreases. This is for 1 mark. You really shouldn't be spending more than 1 minute for 1 mark at all. Okay. Next question. So so again, use the information in the table to explain how the structure and bonding in oxygen differs from structure and bonding in polonium. Okay, so oxygen is your case study. Very nice and straightforward. You know it is simple molecular. Okay, so all the properties of simple molecules apply to oxygen, which is very nice and well. Polonium is not your case study, but it's a use information in the table. Using the information in the table, you could see the electrical conductivity of polonium is very good. Electrical conductivity of polonium is good. So this is not simple molecular because it conducts electricity in the solid state. It conducts electricity in the solid state. This is not simple molecular. Okay, the density is fairly high, quite high, yeah? And then the melting point and the boiling point is considered high as well. They are not like negative value, they are in the positive hundreds region. Okay, and therefore because of this simple fact coupled with high melting and boiling point as well as high density, I'm pretty sure that polonium is a metal. Polonium is a metal because it conducts electricity as a solid. All right, so polonium is going to have a giant metallic structure based on the conductivity as well as the melting and boiling points. Okay, so oxygen has a simple molecular structure. They want structure and bonding, right? So simple molecular structure with oxygen, oxygen, covalent bond. So I show the display formula. Okay, it has low melting point. What is the melting point of oxygen from the table? The melting point of oxygen is -219. So write that down. -219 degrees Celsius and low boiling point. So I'm using the data in the table. Okay, so -183 for the boiling point. So they are not asking us to explain why it has low melting and boiling point. They're asking us how the structure is different. And the structure is different based on the difference in properties, which is a result of the structure itself. I've just mentioned the bonding, but the low melting and low boiling point because of the structure. Because melting or boiling only breaks weak intermolecular forces. You don't break the covalent bond because the structure is simple molecular structure. You break the intermolecular forces between the molecules. Okay, so polonium must have giant metallic structure. So I mentioned the structure first, with metallic bonds between cations and C of delocalized valence electron. It has free electron. It has free, why did I write double S? It has free or mobile. You can write free, you can write mobile electrons to conduct electricity in the solid state. I think I've written too much actually. I think if there's one thing I can skip, I can probably skip this explanation. Okay, probably can skip. Because for 2 marks, you really have to spend some time talking about the structure and the bonding and the data for oxygen. And you have to talk about the structure and the bonding and the data, which is to do with conduction of electricity in the solid state for polonium. So the nonmetals do not conduct electricity, such as oxygen, but going down the group, the electric conductivity increases, become very good in the solid state because it's no longer simple molecular. Coupled with a high melting and boiling point, coupled with a high density, this represents most likely polonium is a metal. It has a giant metallic structure. So moving on to the next question. So part of the structure of carbon dioxide is your case study. Calcium carbide is not your case study, but looking at Ca2 plus and C2 minus. So I hope you can see this transfer. It has lost 2 electrons. This one gained 2 electrons. So 2 and 2, the LCM is 1 and 1. So the formula of calcium carbide is Ca2 plus, 1 of it, C2 2 minus, 1 of it, so it's CaC2. Okay, so this is definitely giant ionic structure. Okay, and this is simple molecular. Explain in terms of structure and bonding why this one has a low boiling point, why this one has a high boiling point. So this is a comparison. So you have to compare the strength of what you are breaking for boiling. Boiling is to do with liquid to gas. All right. So structure your thing. This is 3 marks. So spend around 3 minutes on it after you read the question carefully. CO2 has a simple molecular structure. So structure and bonding, right? So boiling, maybe I should mention about the bonding first, okay? With covalent bond between carbon and oxygen atoms. But boiling CO2 breaks only weak intermolecular forces. Intermolecular mean between the molecules you have forces of attraction, so doesn't really require a lot of energy. Okay, does not need a lot of energy. Therefore, low boiling point. Now onto the second bit, which is to do with calcium carbide. So calcium carbide, as you could see in the diagram above, it definitely has a giant ionic structure. Okay, so giant is essential, ionic is essentially, with strong ionic bonds. But ionic bond is between the oppositely charged ion, so specified in the context of the example, which is Ca2 plus and the C22 minus ions. They are both oppositely charged ions, and with strong ionic bonds between the ions, they need to be broken. Because when you want to go from liquid to gas, you're going from something where the particles can slide past each other but still pretty close to each other but not tightly packed, to gaseous particle that are very far apart, moving randomly at very high speed. So you need to break the attraction between the ions in the liquid state. All right, that needs to be broken for boiling, requiring large amount of energy. Actually, just by writing these two is still not enough. You really must compare. We have not compared yet. We have just stated for CO2 and calcium carbide on its own. Lastly, we need to compare why this one is high, why this one is low. All right, so breaking strong ionic bond. So just make a very short statement. Breaking strong ionic bond require so much more energy than breaking weak intermolecular forces of attraction between simple molecules. So these are individual discrete molecules, and you could count covalent bond because covalent bonds are directional. These are ionic bond, and ionic bond is a force field, and you cannot count ionic bond. All right, it's a force field. Okay, moving on to the next question. So this is pretty similar to the group 6 chemistry we saw earlier, except this is to do with group 5, so 5 valence electrons. This is a table of properties, physical properties such as melting point, boiling point, and electrical conductivity when solid. This is called physical properties. Sometimes question will say, suggest some physical properties of simple molecular compound, or of metals, or of this ionic compound, etc., etc. Predict the physical state of nitrogen. So nitrogen has a melting point and boiling point like that. So we're going to do something similar to the previous question. So this is minus 210, this is melting point. This is minus 196, this is boiling point. If it is in between the melting point and boiling point, it's liquid. If you have passed the boiling point, you are gas. If you haven't passed the melting point, you must be a solid. So minus 200 degrees Celsius, it's somewhere there. Doesn't need to be super exact, but you know. So it's a liquid because I'll use a slightly different explanation to above, but it's the same way I've explained above. Basically, minus 200 degrees Celsius is between melting point and boiling point. Therefore, it's a liquid. Or I can say because minus 200 degrees Celsius is higher than its melting point, which is minus 210 degrees Celsius. Use the information in the table, right? So I'm already using it. Perhaps I could write it down there. Minus 210 degrees Celsius. So it has already melted. So, but it is lower. It's lower. Basically, minus 200 degrees Celsius is lower than its boiling point. So you already melted, but you haven't boiled. So the boiling point is minus 106 degrees Celsius from the data given. Here they use the word predict. Previous question, they use the word suggest. They mean the same thing, right? So arsenic has the melting point missing. So they want the melting point. So I'm looking for melting point. From here to here is around, I don't know. So minus 210 to 220 is around 200. And then there's around plus 240. Okay, give or take around plus 250, sorry. From here to here, it decreased. So I guess between 44 and 630, there's around 600 degrees Celsius. If you add 300, so plus 300 should be all right, I guess, somewhere in between, give or take. So somewhere around 350, I would say, 350 degrees Celsius. I don't exactly know the exact value, but because it's a temperature, a melting point, make sure that you put a unit, because this is normal science, this is basic science. You must have units for temperature or any other physical units, physical quantity that have units. You must include the units. This 350 is somewhere in between. It's not lower than that, it's not higher than this, it's somewhere in between. It seems like going down the group, there's an anomalous melting point there, and we can think about it in the just like the previous question, in terms of electrical conductivity changing, because it's no longer simple molecular. Most likely, this one has become a giant metallic structure. So bismuth, as I said, different conductivity there. So you got to use the information in the table. How the structure and bonding differ. I think I wrote too much for the previous question, which was quite similar. So for these 2 marks, I'll aim to spend no more than 2 minutes. But I want to cover nitrogen, I want to cover bismuth, and I want to explain a little bit, but also both structure and bonding. Okay, so nitrogen has simple molecular structure. With covalent bond between nitrogen atoms. As you know, this is your case study, nitrogen-nitrogen triple bond. Okay, law, melting, and boiling point. These are from the table. See table above. Okay, due to breaking only weak. Do I want to say that? Maybe I can use the electrical conductivity this time, okay? So they are more than just the melting and boiling points to tell you the structure as well, yeah, okay? So maybe I can use the electrical conductivity here, which is not conductor when solid, okay? So law, melting and boiling points, and does not conduct in the solid state. So does not conduct in the solid state could also mean it's ionic compound, because no free ions, right, in the solid state to move, and therefore cannot conduct in the solid state for ionic compound. But it has low melting and boiling point, so together with this, it cannot be ionic, it has to be simple molecular. The next bit is bismuth. So bismuth must have giant metallic structure, as I mentioned a few minutes ago, because looking at the electrical conductivity with metallic bond between, maybe I don't want to specify too much, but it's a metallic bond between the cations and the sea of delocalized valence electrons. The key thing really is it conducts in the solid state, and it has high melting and boiling point. So it conducts electricity in the solid state, and it has very high melting and boiling point. Probably don't need the very, but high melting and boiling point together with conduction of electricity in the solid state point to it being metallic, giant metallic structure instead of being simple molecular. Okay, Anyway, moving on. So chlorine, bromine, iodine, they all exist as this diatomic molecule. Diatomic because they are two atoms making up one such molecule. Chlorine, Br, I. So later on in group 7 chemistry, which is a topic on its own, this is a gas at 25 degrees Celsius, which is room temperature. This is a liquid and this is a solid. This question is basically asking you on why this is a gas and this is a liquid. So this is different boiling point. So even though it's asking you on states of matter, but in essence it's actually asking you on explain in terms of structure and bonding. So this kind of question come in various forms. Structure and bonding can be asked in terms of states of matter such as this. All right. So CO2. Sorry, maybe I just start by saying both of them. Both CO2 and Br2 have simple molecular structure. So because of their structure, simple molecular structures, so I need to talk about boiling. So boiling them requires breaking weak intermolecular forces between the molecule. Intermolecular forces between the molecules. Okay, down group 7, greater, or you can say more, total number of electrons. So this is something that I'll revisit when we come to group 7, but the intermolecular forces, the strength of it depends on the total number of electrons. As you can imagine, going down the group 7, this bromine atom would have more proton than chlorine atom. So bromine molecule would have more proton than chlorine molecule. So bromine molecule would have greater total number of electrons than chlorine molecule. Counting number of protons and electrons are from the previous topic on atomic structure. So greater total number of electrons, therefore stronger intermolecular forces. And if stronger intermolecular forces, therefore more energy to break for boiling Br2 than CO2. Okay, so I do not need to repeat the question again. If I need more energy to break to boil Br2, therefore Br2 remains a liquid, but I need lesser energy to break the intermolecular forces between CO2 because CO2 has lesser total number of electrons. Therefore, CO2 has a lower boiling point. So it's a gas there because lower boiling point than Br2. Okay. Phew, okay, this checkpoint is getting very long now, so I should probably speed up a little bit. So sodium oxide, magnesium oxide, aluminium oxide, they are all giant ionic structure. Don't worry too much about the nature of oxide. This will come under the topic of periodicity, which is basically studying the periodic table in greater detail. SiO2 is the formula for silicon 4 oxide. This is your case study, meaning you cannot afford to forget about it at all. Okay, so this is actually covalent bonding, but its structure is giant molecular structure. Okay, SO3 is a covalent molecule. It's got covalent bonding, but it's actually simple molecular because just looking at its boiling point, this is very low. Okay, not very high. This is lesser than 50 degrees Celsius. It's very low, therefore telling you it's simple molecular. Okay, so these three, we know it being giant ionic structure simply because, well, metal atom, so it has metal and it has non-metal. The non-metal gain electrons, giving O2 minus. The metal will be Na plus, Mg2 plus, Al3 plus. Okay, so that's how you get the formula Na2O, okay, MgO, NaL2O3. All of these you should be able to draw the dot and cross and get the stoichiometry based on the charges being balanced out, because ionic compound contain ions which are charged, but ionic compound itself is uncharged. Okay, so this is giant ionic, this is giant ionic. It seems redundant, but I would imagine that if you write giant and simple, they would have been alright as well, because they would imply giant ionic, giant ionic, giant ionic, giant covalent, simple covalent. Okay, but it doesn't hurt to explain it a bit better. SiO2, as I mentioned, is your case study. SO3 is something you might not have seen before, but sulfur is in group 6. It's got 6 outer shell electrons, 3 oxygen. Oxygen form 2 covalent bond. Oxygen form 2 covalent bond. Oxygen form 2 covalent bond because it's got no OH or whatever. Now you look here, sulfur here, 1, 2, 3, 4, 5, 6. Sulfur has 6 valence electron. It used all of them for bonding. The other thing you need to keep an eye out for is sulfur now has 2, 4, 6, 8, 10, 12. So sulfur has 12 electrons. 12 electrons total in outer shell. After sharing, and is that allowed? Well, you need to think carefully. Sulfur is in the third period. Third period, maximum is 18 electrons. Okay, it's not actually 8 electrons, it's actually 18 electrons, as I would have corrected earlier in the class a couple of weeks ago. So first period, definitely the first shell only accommodate up to 2 electrons. Second period will never be able to do this, because second period up to second shell only 8 electrons. Third period is the third shell. It can accommodate up to 18 electrons. So sulfur is in third period, and it uses all the 6 valence electron for bonding. So it's perfectly legit. Going from here, display formula which is correct, you can get the dot and cross easily. Okay. Anyway, this question is asking you to compare boiling point for 3 marks. Structure and what are you breaking to boil this one. Structure and what are you breaking to boil this one. This is a comparison. Why is this one much higher? So compare what you are breaking here versus what you are breaking there. Which one is stronger that you are breaking? Which one requires more energy to break? Okay, so SiO2 has giant molecular structure. So boiling SiO2 requires breaking many strong covalent bonds. This is how you explain for melting or for boiling giant molecular structure. So we are breaking many strong covalent bonds for giant molecular structure, and this is between silicon and oxygen atoms. Okay, I don't want to say, I don't want to compare them yet, so I'll start by talking about SO3 first. SO3 has simple molecular structure. Simple molecular structure. So boiling SO3 requires breaking weak intermolecular forces of attraction. Okay, so we are talking about the forces of attraction between the molecules. Finally, you need to compare, because it's the comparison that matter. Okay, so breaking strong covalent bond require so much more energy than breaking weak intermolecular forces. That is why one of them, SiO2, has a much higher boiling point than the other one. Now the next bit is on structure of a metal. So I haven't talked too much on the structure of a metal, but structure of a metal consists of the metal cation. suspended in a sea of delocalized valence electrons. So be very careful that you know that it's always valence electrons, and you have to include it in your answer. So refer to this structure why metals are malleable. Malleable means you can hammer it into thin sheet. The fact that you have to hammer it means applying force. All right, so applying force to metals make the layered structure. So these are considered layered structure, where the cations are not straight away touching the cations because they repel each other. Instead, you have the electrons in between that can help you to get attracted. Okay, so there's a force attraction there. Make the layered structure as seen above. Slide over each other easily. Therefore, applying force is when you hammer it and you have a layered structure, so they can slide over each other easily. So this one can go there, this one can go there, or this one can go here, this one can go there. All right. Why metals conduct electricity? Well, because the structure shown, giant metallic structure, above, shows free valence electrons are mobile, okay, or can move, okay, therefore can conduct. Electricity is to do with current, so current is a flow of electrons, and if you have free electrons, in this case, then you can conduct electricity. In the case of ionic compounds, when you're aqueous or when you're in the liquid state, you have free ions, and they can also conduct electricity. So this is the last part of this checkpoint questions, so nearing the end there, so I hope you're still okay. So these are melting point of group 2 oxides. So the group 2, so be careful, you should change this to 2, the Roman numeral. So group 2 cations would be Mg2+, Ca2+, Sr2+, Pa2+. Then the oxide is O2-, 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 O2-. All of them, they have this general formula, group 2 oxide. M2+, O2-, so 1M and 1O. The trend, okay? So melting point of group 2 oxides decreases down group 2. Why? These are all ionic compound, okay? So in all of these giant ionic structure, so what are we breaking? Melting needs to break the strong ionic bond between the oppositely charged ions, okay? So the cations are getting bigger in size, down group 2 because of more filled inner electron shells. So you have more and more electron shells, right, as you go down to each group, and therefore the cations are getting bigger, so the ionic bond between M2+ and O2- are getting weaker. If they are getting weaker, so lesser energy is required. Lesser energy is required to break, okay, to break the ionic bonds between the ions. So here it's not really enough just to talk about, oh, giant ionic structure, oh, break strong ionic bond, because all of these are ionic bonds. So this question is really asking you, compare the strength of ionic bond. Compare the strength of ionic bond. Think about the anion is the same, the cation charge is the same. So unlike the previous question where you have different charge on the cation, different charge on the anion, here the only thing that is different is the cation itself going down each group, the size is getting bigger because you are filling in more and more shells, and therefore when you're filling more and more shells, your valence electrons are further and further away from the nucleus, and obviously the more shells you have, the weaker the ionic bond, because this cations and anions that are attracted as a result of the charges in the nucleus as well as the charges of the electron as well. Next question. So magnesium silicide, Mg2Si, you need to draw outer electrons, or sometimes they call it valence electrons, present in a formula unit of Mg2Si. So if you assume it's ionic, then you know it's Mg2 plus because it's a group 2 metal forming a cations. Group 2 metal loses electrons. You will lose 2 electrons. And how many do you have? You have 2 of it. So therefore, the overall compound is uncharged. Ionic compounds contain ions and they're uncharged. If this is 2 times 2 plus and you have 1 of this, so meaning to say the Si itself must be 4 minus. There's no other charge that can make it, cancelling out the 2 times plus 2 when you only have 1 of it. Okay, so I'll draw magnesium first. So nice and easy. When you lose the outer shell, now you have 2 in the first shell, you have 8 in the second shell, and that is all you have. Do not forget that it is a charge, and do not forget that you have 2 of them. So make sure that you draw 2 of them. I have it nice and easy because I get to paste it, all right? But you probably doesn't have that luxury at all. So again, I have made a mistake because outer electrons only. So I don't need to show the inner electron. I just need to show valence electrons only. So silicon then. Silicon, I'll use a dot to represent the 4 original electrons in a group 4 element. Silicon is below carbon, group 4 elements, 4 outer shell electrons. And then one silicon will accept 4 electrons because 2 come from this one, 2 come from this one. Well, basically 2 come from one magnesium, 2 come from another magnesium, and then again 4 electrons, so it's 4 minus. Okay, and that is quite easy, 2 marks, so avoid losing unnecessary marks and avoid not reading questions when they only ask you to draw outer shell electrons. So last questions in this checkpoint, a reference to structure and bonding. Why SiH4 is a gas. When you are a gas at room temperature, which is 25 degrees Celsius, you already boil before 25 degrees Celsius. So SiH4 must have simple molecular structure. So I've already mentioned about the structure. But if you have simple molecular structure, you must have covalent bond. You must have covalent bond between the atom, between the silicon and hydrogen atoms. However, its low boiling point, i.e. a gas at room temperature and pressure, means we only break weak intermolecular forces of attraction between the SiH4 molecules. If you draw SiH4, okay, and if I draw another SiH4, remember that simple covalent molecules or simple molecular structure. So between this molecule and the other molecules, you have forces of attraction. This is called intermolecular forces of attraction. But within this one, you have covalent bond. So covalent bonds are way stronger than intermolecular forces of attraction, which is between discrete individual molecules, and you only get discrete individual molecules if you have simple molecular structure. Okay, so I mentioned structure, I mentioned what bonding you have between what and what, but the low boiling point means what are we breaking? We're only breaking weak intermolecular forces between the molecules because we separate the molecule further and further apart from each other as we boil it, and this is very weak intermolecular forces, so we only require small amount of energy. So only small amount of energy is required to break the weak intermolecular forces. Therefore, it has low boiling point. Therefore, it's a gas at room temperature and pressure. Okay, so that's it for this tutorial video. which is getting quite long now for these structure questions of structure and bonding. We have covered giant metallic, giant molecular, simple molecular, as well as giant ionic structure. And these kind of questions will always appear in any 14 to 16 years old curriculum, whether you're doing the IGCSE, GCSE, or the O-level. In fact, they will also appear in A-level chemistry as well. So thank you for watching, and ask me any questions if you're unsure about anything, but do use your textbooks, do read up a bit more, as well as practice these type of questions. And you can watch my other tutorial video as well to see what other type of question could be asked, but they all revolve around structure and bonding, and therefore what do you break, okay, for melting and boiling. See you in the next video. So thank you for watching again.